I think it's fine, Andres. Right, very good.
Oh,
Yeah,
okay. So do you see now the second slide?
Yes, yes, very good.
Okay, okay. So on this second slide are those three references I listed. First, the link for the Clifford algebra tutorial, then the article of Giorgio Vassallo, Maxwell's equations and Occam's razor, and thirdly, our book titled Protons and Neutrons, Internal Structures. Okay, so let's then go on to the topic of gaugeless electromagnetism. So in electromagnetism, we start from the vector potential field, and then we apply space-time derivative on it, and we get electromagnetic fields normally. In our case, electromagnetic fields and charges. So let's see how we do it. This sigma symbol is our space-time derivation operator. And it's quite the usual mathematical operator. And these gamma bases, they are the Clifford basis vectors. So when we apply the space-time derivative operator to the vector potential, then we are actually applying it in a Clifford multiplication sense. And when you do a Clifford product, there are two components. The first one is a dot product, which is symmetric. The second part is the wedge product, which is anti-symmetric. And these two parts, they also have a different dimension. The dot product, it comes out to a scalar, and the wedge product comes out to a so-called bivector. Now, this bivector, which we use now the symbol F, it contains electromagnetic fields, and this is quite a standard practice in electromagnetism to use this formulation. However, in standard electromagnetism, the goal has been to apply some kind of a gauge to get rid of this scalar which naturally arises. Now, if you have
maybe ask you during your presentation, is it okay? Andres?
Yeah. You mean to ask questions? Yeah, sure. Yes. If it's short questions, you can always ask short questions. Yes.
Right, because you are speaking about the standard approach, right? So you are still speaking about the classical electromagnetism.
Yes. It's classical electromagnetism, except we don't want to get rid of the scalar term.
Yeah. Okay.
Yeah. So in classical electromagnetism, the gauge is applied with the aim of getting rid of the scalar term, and here what we do is that we do not want to get rid of it, because we can see that mathematically it arises naturally. So if it arises naturally, it probably has some significance or role. And what we do with this scalar term, you can see here, we assign the current density and charge density to the derivatives of the scalar field. So to the spatial derivatives, we identify the spatial derivatives of scalar field with current density, and we identify the time derivative of scalar field with the charge density. So these are quite straightforward identifications. And when we do this identification, then a very interesting thing happens. Now you can express Maxwell's equation in a mathematically very simple way. So we had this expression of electromagnetic fields and charges that I showed in previous slide, and we apply again the space-time derivative. And what we get is that we find that the space-time derivative of the fields is zero. Or put it another way, applying 2 times the space-time derivative to the vector potential gives you 0. And
that's Andres, that's identical to the quaternion formulation, isn't it, or not?
It's probably similar. I have not studied quaternion formulation, but probably similar, because Clifford algebra is very close to the quaternion formulation.
Because I think it's the same.
Yes, yes, yes. So you can work out the algebra in that reference I showed in the beginning. The algebra is discussed in detail, but once you work out the algebra, you find that this simple differential equation is exactly Maxwell's equation. And I think this is amazing that in the end, Maxwell's equation has this mathematically simple, you could say beautiful form. And so what do we see here happening? Historically, the charges were inserted as external objects into Maxwell's equation, and because charges were put in as external unidentified objects, the electromagnetic gauges were imposed on those to get rid of any scalars that were just messing up the Maxwell's equations. But now we do not have to put in by hand any charges, because what we see is that gaugeless electrodynamics is a simplified theory, and it is a proper field theory because the electromagnetic fields we work here contain the term for the charges as well. So we have a proper field theory formulation that includes both fields and charges, and all is described by this simple differential equation. So this is quite encouraging that to study further whether this could be the right formulation of electromagnetism. Now, one consequence of this formulation we can see right away is that charges move at the speed of light. Let's see how to show that. The first line you see here is the electric current 4 vector. This is basically just the definition of the identifying electric current with the scalar field derivatives. So I showed you this definition 2 slides ago. And then we can apply charge conservation on this current vector by taking the space-time derivatives with a dot product. So when you take it with a dot product, then basically you see that the current flowing in or out for any point is just the time derivative of charge density, and this has to be 0 because of charge conservation. Now, because we have a scalar field, then applying the space-time derivative with a dot product is actually the whole derivative. So what we have seen is that taking the second derivative of scalar field gives you a 0, and this can be understood as a wave equation, right? So, and this wave equation has the straightforward solution. It shows that the scalar field S moves with the speed c, speed of light. And the movement of electric charge with the speed of light in the context of electrons has been recognized about 100 years ago. And Schrödinger gave the name Zitterbewegung to the speed of light oscillation of charges. But at that time, Schrödinger recognized this phenomenon, but he could not identify the mathematics behind it. But now we can see that the mathematics is quite straightforward, that prescribes that Zitterbewegung must exist. Okay, so we have this helical internal motion of the electron charge, and let's now focus on the experimental data to quantify how does the electron charge really move in practice. And we start from the electron because to understand anything later about nuclear structures, we first have to clarify exactly what the electron is and how the electron dynamics works out. Now, the electron has been studied quite a lot via light scattering experiments. And here you see the concept of light scattering, of how incoming light wave reacts with electron, and then there is an outgoing accelerated electron, and outgoing light at a different direction and frequency. Now, the phenomenology of light scattering depends on the light frequency relative to the electron mass. With a low frequency light, we have the Thomson scattering phenomenon, and with a high frequency light, we have the Compton scattering, and the Compton scattering is described by the so-called Klein-Nishina formula. So by applying Klein-Nishina formula to this experimental scattering cross-section, we can measure the spherical charge radius of the electron, and the experimental data gives this 2.82 femtometer spherical charge radius, and this 2.82 femtometer is well known in physics. This value is referred to as the classical electron radius. Okay, so the experiment tells us this is how large electron charge is. So now let's apply our electromagnetic theory and calculate what is the electric field energy when we integrate it from infinity down to this charged surface. So this expression is the integral of electric field energy. And when you do this integration, the answer you get is 255.5 kiloelectron-volt electric field energy. So that's an interesting number, because you may recognize this is exactly 1/2 of the electron mass, right?
Yeah. You know, this calculation is classical again, right?
Yes, yes. Everything, everything is classical.
Yeah.
Because this experiment, directly measures electron radius, and once we know the electron radius, we can apply Maxwell's equation.
Yes.
I assume your question refers to, what about quantum mechanics? Well, quantum mechanics has to be compatible with Maxwell's equation. So, of course, electron wave function follows quantum mechanics, but that does not mean Maxwell's equation is not valid. Maxwell's equation always must be valid. So this calculation in every circumstance gives us half of the electron mass. All right. Then in order to find the other half of electron mass, we have to consider what kind of oscillation the electron is doing. So I mentioned that, I mentioned that Schrödinger gave this name Zitterbewegung for the light speed oscillation of the electron, and de Broglie was the first one who suggested what frequency to assign to it. De Broglie suggested to assign the electron energy divided by the Planck constant as the frequency of this very fast oscillation. So let's see what happens if we assign this frequency and then look at the electron from a boosted reference frame. So the Zitterbewegung is an oscillation in time, and when we look at it from boosted reference frame, the Lorentz boost mixes time and space coordinates according to this mixing matrix, where you see the sin h and cos h expressions, and W is the rapidity. Rapidity is the Lorentz boost parameter times the beta, which is electron speed over c. Well, this is relativity basics, and so when you apply this to the frequency, then this is the formula of the wave number divided by 2 pi. So basically, the wave number comes from two parts. The first part is the frequency of the Zitterbewegung oscillation. The second part is this sin h expression. So for the first part, the frequency part, we apply de Broglie's prescription of electron mass over h. For the second part, we use this mathematical, let's say, definition. This you can look up in any general relativity text, that the sign h of rapidity is the gamma Lorentz factor times beta. And when we write it out, then we get this expression. So we are basically done. We rearrange the terms and calculate what h bar times k is. And what we find is two factors. First is this gamma Lorentz boost factor times the electron rest mass, and the second one is electron speed. This first part we recognize as the relativistic electron mass. So mass times speed is the electron kinetic energy. So what we found after doing a simple Lorentz boost transformation is that there is a spatial wave that is appearing, and the wave number of this wave is exactly given by the electron's momentum. Now this expression you can recognize as the basic postulate of quantum mechanics. However, we don't have to think of it as a postulate. We can think of it the opposite way. We can say that all of the quantum mechanics experiments which verify this relationship of the quantum mechanical wave number are actually proofs that the Zitterbewegung oscillation is real and de Broglie's frequency assignment is correct. So we can consider the quantum mechanical wave phenomenon as a proof for the reality of this Zitterbewegung frequency. Okay, so we know that the electron charge moves at the speed of light. Now we also know its frequency from quantum mechanics. And the electron charge moves on a circular path so that it creates the spin of the electron. And we have all the parameters now to calculate the radius of this light speed circulation, because we know the frequency, we know the speed. So once we put those in, we get the Zitterbewegung radius of 386 femtometers. So that's again a well-known length in physics, because this is being referred to as the reduced Compton radius. So once we know this circulation radius, we know the current that is flowing in this electron current loop, and then we can calculate the corresponding magnetic field energy. So once we calculate the magnetic field energy from the current loop formula, we have an amazing surprise. The magnetic field energy turns out to be exactly 255.5 kilo electron volt. So it means that we found the second half of the electron mass. So our conclusion is the electron mass is nothing else than electromagnetic field energy. Half of it is electric field energy that we calculated previously, and the other half is the magnetic field energy that we calculated from this loop formula. And the two are exactly equal because we have an induction phenomenon. The electric and magnetic fields continuously induce each other in the electron. What is also very important to remember in this formula is that the magnetic field energy and thereby electron mass is inversely proportional with the Zitterbewegung radius. This will be very important later to remember the inverse proportionality between particle mass and Zitterbewegung radius. Also, what you can notice is that you can calculate the magnetic field by applying the flux formula. So magnetic field energy is 1/2 times magnetic flux times electric current. And this second part, the magnetic flux, is h/e. So Planck constant over elementary charge gives you the magnetic flux of this electron Zitterbewegung loop. And remembering that flux is h/e will be also important when we go forward. Okay, so now we have a reasonable
a
understanding. Yes.
small question before you continue? Can you
Yes,
say,
please ask.
can you say a little bit more how you say these two are induced one into each other? Is that the internal electron oscillation of like the matter wave that De Broglie was talking about? So you talked about
Yeah,
induction briefly.
in a way, yes. There will be next slide about it.
Okay.
Basically, the induction happens on this Zitterbewegung circle. So somehow the Zitterbewegung circle, where the scalar field is non-zero, is the place where the induction happens. But the details are not so straightforward to grasp. I have been using here very simple formulas, but that's I think a deep question, exactly where and how this
Because
induction
this
happens.
velocity isn't changing, right? In the Zitterbewegung, right?
Yeah, the electron charge always moves at the speed of light,
So you
but
would say there is no induction if it's a constant velocity.
uh,
Or it's
but there is
continuous, or is it
the
continuously
topology
changing?
defines the induction. So the point is that the uh, induction is not because of charge acceleration, but the induction is defined by this topology where you have this circle with
No,
non-zero scalar field.
but, but let me ask you some. What do you mean? Induction is not you are not because you are not seeing the time derivative here.
Well, Andras says it's a beautiful thing that you can derive one half of the mass by means of the electric field and the other mass by means of this
Magnetic field.
and then, but they are one is induced into another, so you would expect some kind of oscillatory behavior of the motion of the electron.
Yeah. I have one slide.
Okay, please continue. Please, it just comes to mind. So please continue.
Yeah. There is going to be a slide where I will give an example how to understand this induction a bit.
Okay.
So I will come back to this question.
But let me ask you still back more general question. So you are saying that I think the Schrödinger would call it Zitterbewegung, right?
Yes.
This Zitterbewegung is induced by the scalar field. Is that correct understanding?
I believe that, yeah, this we can understand it that way. And when the scalar field disappears, for example, if you have an electron-positron annihilation, then the oppositely charged scalar fields annihilate each other. Then the induction becomes trivial because you see two photons flying out.
Right, but if just to wrap my mind about that, so you have a standard Maxwell equations here, and you can simplify them either in some Clifford algebra or quaternion, whatever, and you get very simple expression of the Maxwell equation in terms of some special derivative, right, of the vector potential, right? And then you say, if we don't gauge out the scalar part, right, a consequence of that, you get a kind of this Zitterbewegung, right?
Exactly.
And also it explains the mass of the electron. Where I like that a lot because the whole notion of particles mass is kind of also a little bit more philosophical, like what it is, right? And I think it's the electromagnetic origin, right? I like
exactly.
that.
Exactly.
It's a beautiful result. This is a beautiful result, right?
Yes. Okay, thank you. So I think you understand the concept exactly. And so this next slide is another check with experiment. The spherical electron charge we derived in the high frequency regime. If you look at the low frequency regime of the Thomson scattering, then experiments show that the Thomson scattering radius is the Compton radius. So again, our theory matches with experiment, because in the low frequency, light is scattering from this whole electron structure. It does not resolve the individual charge circle anymore. Okay, and here, now next slide is talking a little bit about this electron wave induction aspect. So the Zitterbewegung you can imagine as a wave going around on this surface of the cylinder, right? And when you look at it from a boosted reference frame, then there are two effects that happen. The first effect that happens in boosted reference frame is that Lorentz contraction shrinks the electron by gamma L along the z-axis, where gamma L is this Lorentz boost factor. But there is a second effect. The second effect is a transversal Doppler shift effect. And the relativistic Doppler shift is again boosting by gamma L, but this transversal Doppler shift is boosting in the x and y directions. So the net effect of these two effects together is that from a boosted reference frame, the electron is isotropically shrinking by gamma L in all directions. So it retains a spherical charge surface, but it just becomes smaller. And here you see an illustration what happens in the rest frame versus boosted frame. So in the rest frame, you see the electron Zitterbewegung going on a circle. The charge doesn't have a speed along z. In a boosted frame, the electron moves in the z direction, and the spherical charge moves along this helix. But the more fast your boost is, the more the electron shrinks into a smaller and smaller helix, and in the limit of speed of light, this actually becomes like a linear motion. So, but now from our point of view, the main point is to remember that Lorentz boost shrinks the electron by this gamma L factor, and the reason why I mentioned that this is an example of the induction, because you have an induction in the wave and you have the Doppler effect appearing in the electromagnetic wave. Okay, so now on the one hand, we saw that a relativistic boost shrinks the electron Zitterbewegung radius by gamma L factor. On the other hand, from the magnetic energy calculation, we saw that the electron mass and magnetic energy is inversely proportional to the Zitterbewegung radius. If you put these two together, then it means that the electron mass is proportional to the Lorentz boost factor, and the formula is here. And this relativistic mass formula is exactly Einstein's formula. So we automatically get Einstein's relativistic mass increase simply by doing Lorentz transformation of the electromagnetic fields. Okay, is that concept clear?
Yeah, I think you can go on.
Okay, that's good. So this has concluded what I wanted to say about the electron. And now that we have a reasonably successful model for the electron, comes the big question. Can we apply something similar to the proton? If it worked well for the electron, why could it not work the same way for the proton? So let's look at the proton via the same methods. So the first question is, what is the spherical proton charge? For the electron, we have been investigating it via Compton scattering. So let's look at the proton Compton scattering data. Here on the bottom right, you see a proton Compton scattering measurement. But the one difference from the electron is that here you see pair creation processes, which are these peaks. This you did not see in the electron because the energy was much lower, But here at high energy, for example, this peak corresponds to pion production. But this is not what we want to look at. What we want to look at is the actual Compton scattering. So we want to see the Klein-Nishina formula integrating with the electron, integrating with the proton Compton radius in the low energy and high energy limits. And when you integrate the Klein-Nishina formula with experimental data in these limits, what you get is 0.0015 femtometer spherical charge radius for the proton. And the Klein-Nishina formula is quite sensitive to the proton radius because it appears as a square in the formula. So as an example, if you would take the proton radius to be 0.005 femtometer, then this red line shows you that the Klein-Nishina formula quite much exceeds experimental data for both low and high energy limits. So this 0.0015 femtometer is quite a reliable estimation. Then the other measurements that experimentalists put a lot of effort is to measure the so-called mean radius of the proton. And this mean radius can be identified with the mean Zitterbewegung radius. And the current consensus data for the mean proton radius is 0.84 femtometer. If you want to go beyond just these mean values, it's possible to look at the high energy scattering data. So this is the high energy scattering distribution from JLab. So what this shows is that the proton is kind of empty in the center, and it has some structure that extends between 1 and 1.5 femtometer, and it has some structure between, and the mean is at 0.84.
There's the electron scattering.
Sorry?
That's the electron scattering data of it.
Yeah, it's high energy electron scattering data from the proton. But this scattering chart in the end reflects the proton structure. Yeah. So I have summarized it with this kind of a donut figure, that you have this tiny proton charge, and then it is somehow doing a Zitterbewegung in this region. Okay, so the first logical question is, can we consider the proton to be simply a very high energy positron that is somehow stabilized at that mass value? Now, specifically, the proton-positron mass ratio is 1836. So if we scale down the positron values by this mass factor, then what would we get? Firstly, we would get the spherical charge radius that is actually matching the experimental data I showed you before. That's good. But you would get the Zitterbewegung radius 0.21 femtometer, and you would get the magnetic moment being 1 nuclear magneton. Now, these last two values are quite different from experiment. They're same order of magnitude, but numerically different, because experimental data shows the following. The charge radius is that value I showed before, which is matching, but the mean Zitterbewegung radius is 0.84, so that's about 4 times larger than scaled positron, and the proton's magnetic moment is 2.79, almost 3 times larger than scaled positron. So these mismatches indicate that the proton is actually not a scaled positron, but something else. And nevertheless, let's try to think what is the minimal change we have to do from positron model to account for these values.
Andreas,
yes?
did you, I can imagine, not the magnetic moment, but the RP, for example, the error bus, the experimental error bus are taken into account somehow?
These are quite precise measurements. So especially the magnetic moment is
Magnetic
quite
moment,
many
yes, yes,
digits.
yeah, it I know.
Yeah, the RP here, the error bars is also quite small. There is discussion whether it's 0.83 or 0.85, 86, but it's only in the last digits, let's say plus or minus 1 or 2. So not big error bars. Okay, so what is then the minimum change we have to do from the positron model? Well, we look at the experimental data to get inspiration, and the article which inspired us is this one that I highlighted, the measurement of an anapole momentum in cesium. The anapole moment is another word for toroidal magnetic moment. So if a nucleon has a toroidal magnetic moment, then maybe its Zitterbewegung topology is actually toroidal. And this is the model we have been working with. So the only change that we do with respect to the positron model is to say that we have a toroidal Zitterbewegung, not a circular. So it's only a topology change of Zitterbewegung. And with that single change, when we calculate the various values, we get these values that are highlighted here. And the detailed calculation is explained in the book, and I will introduce it also in this presentation. But you can see that when you look at these numbers, that we match very nicely the spherical charge radius, and also the toroidal radius we can identify with the so-called proton radius. There is a 99% exact match. And the magnetic moment also comes out very close to the measured one. And in the following slides, I will show you how to calculate two of these values. So the first calculation, that is the very simple one, is the proton's spherical charge radius calculation, because we do the same method as before. We assign half of the proton mass to electric field energy, and when you require this electric field energy integral to give you half of the proton mass, then you obtain 0.0015 femtometer spherical charge radius, exactly the value that integrates with experimental data. So the next challenge is to calculate the Zitterbewegung radius, but to do that, we have to know somehow the ratio of the poloidal versus toroidal Zitterbewegung speed. Now, I argue that the correct assignment is that the poloidal and toroidal Zitterbewegung speeds are the same, and the same value is then c over square root of 2. The reason why it's c over square root of 2, that these are orthogonal vectors, and with this value, you have two orthogonal vectors, so the net speed of the proton charge is exactly then c, which is required by Maxwell's equation. So one argument to assign this value is the symmetry argument. So then the poloidal and toroidal Zitterbewegung speeds are somehow symmetric. But an even more strong argument is to consider the Thomas precession effect. So you have a poloidal circulation and a toroidal circulation. Each one has c over square root 2 speed. And you can imagine a thought experiment that instead of looking at it from the lab frame, you want to catch up with the toroidal oscillation and look at it from a rotating reference frame in which this toroidal oscillation disappears. In other words, you are trying to catch up with this toroidal circulation. So you have this c over square root 2, the lab speed, and in the rotating reference frame, the so-called real speed is the beta prime over the gamma Lorentz boost factor that you have to apply to catch up with the circulation. So this is the well-known Thomas precession effect formula. And when you put in the numbers, what is the speed you have to go to catch up with the toroidal circulation, you can see that the speed you have to go is actually the speed of light. So you would have to rotate as fast as the speed of light due to the Thomas precession effect to catch up with the proton. And you can see that this is exactly what we want, because this means that we have a proper Zitterbewegung in the toroidal direction, which is actually the speed of light in the rotating reference frame. So, okay, so therefore, for this argument, we assign the c over square root of 2 to the poloidal and toroidal speeds. Also, let us keep in mind that for every Zitterbewegung loop, we have the magnetic flux that is quantized to h over E value. And if you consider, for example, a hydrogen, then you can see that in a hydrogen atom, the proton charge is even moving in 3 loops. You can say circle over circle over circle. You have the poloidal Zitterbewegung loop, you have the toroidal Zitterbewegung loop, and then the electron and proton, they move around their shared center of mass. So you have also this Bohr orbital loop. And somehow this is the nature of Zitterbewegung and quantum mechanics, that you have these standing waves, and the standing waves is actually not just a simple wave, but what nature gives you is this circle over circle over circle, almost like a fractal type of waves, which is somehow stabilized. And the big question that is not yet answered today, what exactly is it that stabilizes this fractal type of charge circulations? But in any case, for the purposes of our presentation, what we have to remember is that for every stable charge circulation, whether you are looking at the quantum mechanical loop or Zitterbewegung loop, the magnetic flux is always h over E. Okay, so with this background, let us go forward to the magnetic energy considerations. The magnetic moment is given by this simple E h bar over 2m formula. And for any particle, when you consider this formula, the only non-constant factor is the particle mass. Everything else is constant. And since you can see that the magnetic moment is inversely proportional to the particle mass, this formula tells you that excess magnetic moment is then related to a fractional magnetic mass in that direction. So in other words, the large magnetic moment is inversely related to the smaller magnetic mass in the toroidal direction. So the total magnetic mass of the proton is half of the proton mass, and the toroidal part of the magnetic mass is then divided. If we take this whole magnetic mass and divide it by the excess magnetic moment, this 2.79 excess magnetic moment factor, and then we find that the toroidal magnetic mass is approximately 168 megaelectron volt. Okay, and then the remaining magnetic mass is the poloidal magnetic mass, that is then given simply by subtraction. Okay, so from the magnetic moment, we can identify what is the toroidal and poloidal part of the magnetic mass. And again, I want to emphasize that the reason why we could do it is that because what we experimentally measure is the toroidal part of the magnetic moment. All right, so now let us apply the same magnetic mass calculation that we used for the electron. So we apply this flux-based magnetic mass calculation. So the magnetic energy is 1/2 flux times the current. As we discussed before, the flux is always just h/e. And when calculating the current, then we have the elementary charge, the Zitterbewegung speed, divided by the circumference. And the Zitterbewegung speed we already know, because in both poloidal and toroidal direction, this is c/√2. So the only unknowns here are the toroidal radius and the poloidal radius. And since we know everything else, we can calculate these values. And what we get is 0.83 femtometer toroidal radius and 0.46 femtometer poloidal radius. So this is quite a satisfying result, because via this simple calculation, we calculated the mean proton radius, which is 99% matches the consensus experimental value. Also, if you consider this poloidal radius, it means that the actual proton torus structure ranges from 0.4 to 1.3 femtometer, and this 0.4 to 1.3 femtometer range is compatible with the scattering measurement results that I showed you before. So okay, so this is then the essence of our proton calculation. Do you have any questions about this?
It's at the very least a peculiar coincidence, at the very least, right?
Yes, many coincidences. Okay, so let's go on then to consider what it means for the neutron. So our results basically established that the proton regains its elementary particle status, and if the proton is an elementary particle, it means that the difference between the proton and the neutron is that the neutron has an additional negative elementary charge, right? So it directly follows from our model that the neutron is a proton plus some kind of a negative elementary charge. And we will refer to the neutron's negative charge as a nuclear electron.
I'm sorry to interrupt you, Andres. Just a short question, practical question. How many slides do you have to go?
I was not looking at the time. I have maybe 10 more slides, but no more calculations. So yeah, I understand I have to speed up, right?
Yeah, another like 10 or 15 minutes, so we can have a discussion afterwards.
Yeah, let's do that. So I will try to wrap up in 10 minutes. And yeah, the rest will be more simple. There will be one more theory slide, and the rest is just experiment. Okay, so I try to speed up. So if the nuclear electron is some kind of a heavy electron in quotes, what kind of reactions there can be? Let's look at the analogy from the muon, because muon is a reasonably well-studied particle. The muon has a decay reaction, and when it decays, then it becomes electron plus neutrino radiation. Well, by using this analogy, it means that the nuclear electron decay produces electron plus neutrino radiation. Okay, that's exactly what we see in neutron decay. So the nuclear beta decay is probably the nuclear electron decay process. Other type of reaction is the capture of this nuclear electron by a proton or other nucleus. So from quantum mechanics point of view, the nuclear capture is just a quantum mechanical state of change, and the QM state of change releases single frequency transversal radiation. So in the electron and proton case, we get a hydrogen plus well-known 13 electron volt. Exactly same process in the muon plus proton case. We get gamma emission and muonic hydrogen. So what we expect is that nuclear electron plus proton also should emit a gamma radiation that accompanies this quantum mechanical state change. So what we will be looking for is the radiated gamma energy signature, and notice from this equation that the radiated gamma energy is exactly the binding energy of nuclear electron capture. Now, what I said about the proton, we can generalize to another isotope, and this is the last theory slide. So if the nuclear electron is captured by some isotope, charge Z, we can write this mass energy balance equation. Incoming nuclear electron mass plus isotope mass equals the outgoing isotope mass plus the radiated gamma energy, just energy conservation. Another way to get the same reaction is to have normal electron plus this isotope mass as input. This is electron capture reaction. Then you get the same outgoing isotope plus the electron capture energy. Now the incoming and outgoing isotopes are the same, so we can just subtract these two equations. And this is the most important to keep in mind, that we have a formula for nuclear electron mass. Nuclear electron mass, by subtracting these two, is nothing else than electron mass plus radiated gamma energy minus electron capture energy. Remember that electron capture energy is negative for most isotopes. Okay, so this is the theory, and now we look for gamma peaks that could give this kind of reaction. The first type of experiment was reported in 2004 by Sergio Focardi and his colleagues. They experimented on nickel under hot hydrogen flow. They detected emission of neutrons plus the appearance of a 661.5 gamma peak, which they could not explain where it is coming from. Also notice that this gamma peak goes down with the time. Its half-life doesn't match any known isotope at this energy. So let's try to consider whether this is the signature of nuclear electron capture with 58 nickel isotope. We apply the formula I explained before. So we know the released gamma energy, we know the electron capture energy for nickel 58, and what we get is 1554 kiloelectron volt. So with this hypothesis, the nuclear electron mass is exactly this value. Okay, second experiment. This is now our own experiment. It's
maybe, Andras, I really need to interrupt you. Short question, there is a well-known problem with neutron mass negative mass deficit. You know what I'm speaking about, right? If you take mass of the proton and mass of the electron, if you sum them up, yes, the mass of the neutron is bigger than that, right?
Yes, because we don't take the mass of electron, we have to add the proton plus this 1554
exactly. So you would explain the negative mass deficit by this nuclear electron much heavier than the yes?
Exactly. It's approximately 3 times heavier than normal electron. Exactly. Yes. So now we actually look exactly at the neutron, because second experiment, which was done by my co-authors, is exactly nuclear electron capture by a proton. So our experiment is a artificial lightning experiment. So what you see here is a humidifier that generates moisture, and we have a 20 kilovolt spark discharge gap. And this whole setup is in a shielded box with a sodium iodide based gamma spectrometer. And this experimental setup has been inspired by these reported lightning experiments. It has been established quite well in the literature that there is a neutron production during lightnings. So there is some kind of a nuclear reaction that lightnings create, and this we wanted to investigate. So when we did this experiment with 20 kilovolts, what we saw is the appearance of a gamma peak at 259.6 kiloelectron volt. So you can see this very nice gamma peak here. And the sodium iodide sensor has some error, but to be as precise as possible, we use the Gauss curve fitting. Here you see the center value that I mentioned, and the error is plus minus 2 kiloelectron volts. Also, we did oscilloscope-based analysis, and we can see that the gamma peaks are time correlated with the spark discharges. So these are really triggered by the spark events. Okay, we apply the same formula I explained before. So we have this electron mass plus this gamma peak energy minus the well-known minus 782 electron capture energy for neutrons. And the result we get is 1553 plus minus 2 kiloelectron volts, exactly the same as before. And now, third experiment, this one I did with the help of a thorium solution. So my idea was that if you have a thorium solution, then you have very high energy alpha particles, 5-6 MeV in the solution flying about, and these high energy alpha particles could knock out nuclear electrons from the thorium core. So this is a very simple playground to experiment with nuclear electrons. Just take a thorium solution if you can get your hands on thorium. And now I don't have time to explain the experimental signature that yes, the experiment seems to show that nuclear electrons exactly knocked out. But I go to the main point. So the main point of the experiment was that I prepared two solutions. One solution with concentrated solution of ammonium nitrate together with thorium nitrate. The other solution did not contain any ammonium nitrate. The solution that has the ammonium nitrate is this red curve. The one without it is the yellow one. And you can see that there is a gamma peak appearing at 886 kiloelectron volts only in case of the ammonium nitrate. So only in case of ammonium ions being present. The other gamma peaks you see here are from the actinium part of the thorium decay chain. Okay, so let's consider whether this peak that is associated with nitrogen-14 is the capture of nuclear electrons on nitrogen-14. So we apply the same formula as before. The gamma energy is 886.6. Here you see the electron capture energy, and you calculate the formula, and you get exactly 1554 kiloelectron volt nuclear electron mass. So I think this is quite nice that we have now three very different experiments, and each of these three experiments gives exactly the same nuclear electron mass. So as said before, at the very least, it's a curious coincidence. I believe that this is the precise measurement of nuclear electron mass particle. And if somebody is skeptical, well, there are many more isotopes in the periodic table. So everybody is welcome to do more experiments with more isotopes and see if you can get a gamma peak at the same or different energy. So our summary is that the existence of nuclear electron is indicated both by proton theory and by experiments. We can precisely measure its mass, and nuclear electron is a short-lived particle in free particle state. That's why we don't see it flying around, but it is stabilized by sufficiently high nuclear binding energy, and that's why we have the heavy nuclei. So that's the summary, and now we have a quite well understood picture of both the proton and the neutron structure, what they really are, as well as the electron. And the details, further theoretical and experimental details, are described in our book, The Protons and Neutrons Internal Structures. And thank you for attention. Now, welcome the questions.